Okay, let's continue. Last time what I did was a gallop, a forced gallop through the fundamentals of general relativity, just meant for refreshing our memory. And also today I think there will be a lot of just repetition of what you have heard before. So the subject will now be the Schwarzschild metric, and in particular Schwarzschild black holes. Okay, but to begin with, I will speak about the Schwarzschild metric in general. It doesn't describe only black holes, as you certainly know, but also the field around spherically symmetric stars, or planets, or whatever, as long as it is spherically symmetric. So what is the Schwarzschild metric? The Schwarzschild metric is a unique, and that's an important thing, the unique solution. It's a unique spherically symmetric solution to Einstein's vacuum equation without a cosmological constant. This means to the equation r mu nu equals 0, which looks harmless, but it is far from being harmless. Yeah, so what is hidden in this short formula is a system of 10 coupled differential equations. Yeah, if you write it out in components, mu and u take values 0, 1, 2, 3. It's symmetric, so there are 10 independent components, 10 equations, and each of the equations is a second order partial differential equation for symmetric components. So you have a coupled system of partial differential equation for 10 unknown functions, the g mu nu's. Well, if you assume spherical symmetry, then the situation is not quite so bad. Then actually, if you just make an ansatz for the metric that is spherically symmetric, you have only 3 functions. Not 10 as in general, you have only 3 functions, which I usually call mu, nu, and sigma. And you have only 3 non-trivial equations. Yeah? So of the 10 equations, 6 become just identities, 0 equals 0. And 2 others become equivalent, so you end up with 3 independent equations for 3 independent equations for 3 unknowns. And well, I think that everybody in the audience has once run through this derivation of the metric through solving this set of equations. So in my GR course, I really did this in nauseating detail, and I'm not going to repeat this here. So I will just write the Schwarzschild metric now on the board. And that's what you find. That is what you find. So the metric G is that it's not one solution, it's a one parameter solution. And the parameter is called RS. So you have a t coordinate, that's the timepiece. Then you have a radial coordinate, squared of course, and then you have an angular part. Because you have spherical symmetry, it must be proportional to the standard metric on the 2-sphere. This is this here, what I've written in bracket there. So this is just a standard Euclidean metric on the 2-sphere in coordinates theta and phi. Then we have a radius coordinate, which is denoted r, and a time coordinate t. And we have the one parameter on which the whole thing depends, which is Rs. And the meaning of where this parameter comes about as an integration constant. Yeah, if you solve a differential equation, then it's very natural. But I forgot a square here. Yeah. Thank you. So then you would expect that at least one integration constant would turn up. Usually you would expect more, but because of the high symmetry here, it's just one integration constant which turns up, and that's the Rs. And if you have found the solution, then of course you have to ask yourself, what's the meaning of this Rs? And the interpretation comes from comparing with the Newtonian theory. So when you discuss a field equation of general relativity, you should also discuss that in a certain limit, this produces a Newtonian theory as an approximation. And for a metric of this form, the Newtonian limit is hidden in this term here. So this term, the deviation from the 1, corresponds to the Newtonian potential in the weak field regime. So you compare this term with a c squared. So you have to take the c squared inside the bracket. Then you compare this with the Newtonian potential, and then you read what the RS is. So from Newtonian limit, you find that this RS is related to the mass of the central body. We have spherical symmetry, so you may think of a spherically symmetric body, and we are talking about the gravitational field outside of this body. And certainly the mass of this should enter, and it is given by this expression. G is Newton's gravitational constant, c is the speed of light, of course, and m is the mass of the central body. So that's what we call the Schwarzschild radius. So the index S stands for Schwarzschild. Yeah, I think in English you don't write it with a hyphen. So the family of metrics is parameterized with the mass of the central body. And of course the metric is valid for a star of radius r star. The metric, of course, is valid only outside of the star. It's a vacuum solution. Yeah, we solved the vacuum equation with a 0 on the right-hand side. So it's not valid inside the star. So it's a star, the metric is valid at R. Well, actually, the radius may depend on time. Yeah, you may consider a pulsating star. That's okay. You just assume spherical symmetry. If you look at the derivation of the metric, you don't need more than spherical symmetry. Actually, Schwarzschild, when he did it in 1916, he assumed that the metric is time independent, but that's not necessary. It comes out this way. So for a star of radius r, the metric is valid at, so r, the radius coordinate, ranges from r star to infinity. And of course, the time coordinate ranges over all of r. And the angle coordinates, theta and phi, they range over the two-sphere, S2, with the usual coordinate singularities. Yeah? So you know that you cannot cover the whole two-sphere with one coordinate system. So, okay, so that's where this metric is valid. And you see that you have no problem with this metric as long as the radius of your star is bigger than the RS. Yeah? But if the radius of your star is smaller than the RS, then you see that you do have a problem. First of all, this thing here changes sign. So for R smaller than RS, this thing, the whole thing becomes positive. And this means T is no longer a time coordinate. Yeah? You can, in this area where R is smaller than RS, you cannot move on a T line. You would have to move with a speed bigger than the speed of light, which is not allowed. So that's the first thing you see, and it's even worse with this term here. You see at R equal RS, you have a 0 in the denominator. And that's always very bad. And so you don't know what to do if you have a star which is smaller than its Schwarzschild radius. Now, fortunately for all stars, planets, and so on, we have this inequality satisfied. So for stars and planets, or whatever else you may think of as a spherically symmetric celestial body, we always have our star. Yeah, well, let's assume that let's allow that it is pulsating, that this is much bigger actually than RS. So let's check for the Earth, for instance. If you insert here the mass of the Earth, who knows what the RS gives? If you just take the constants from a table. About a centimeter, even less than a centimeter. And the radius of the Earth is 6,000 kilometers, so it's considerably bigger. Yeah? And for the Sun, who knows for the Sun the Schwarzschild radius? Everybody should know this actually. So a few kilometers, yeah, something like 3 kilometers. And the radius of the Sun? 700,000 kilometers, yeah. And so you can check all the celestial bodies and you will always find that the Schwarzschild radius is much, much smaller than the physical radius of the thing. So this singularity here and this change of the sign is irrelevant for this situation, because in the range where the metric is valid, you do not have this singularity. But you can think about bodies where actually where the Schwarzschild radius is bigger than the physical radius, and then we get a black hole, and that's what we will discuss in a minute. But before doing this, I want to list some other properties of the Schwarzschild metric. So for the time being, let's assume that this is satisfied, that we are only in the region where the metric has no pathologies. And then let's talk a little bit about properties of this metric. So properties of the Schwarzschild metric. First thing I want to mention is that the metric is what is called asymptotically flat. What is meant by this is the following. If you go into the region where R is very big, so if you are far away from your central body, then in particular the R is very big in comparison to the RS. This means this term, RS over R, can be neglected in comparison to the 1. So then this is a good approximation. And also this is a good approximation. And what you see then is just our good old Minkowski metric in spherical coordinates. Yeah? If you neglect these terms here, then you get exactly Minkowski space if RS is 0, if you don't have any mass. Yeah? Then you get exactly Minkowski space. And if the M is non-zero, then you get approximately Minkowski space far away from the central body. And that's usually phrased in the way that one says the metric is asymptotically flat. And that's an assumption which the metric of an isolated body should satisfy. Yeah? If you neglect the influence of all the other masses on the gravitational field, if you just think of one body completely isolated in the universe, no cosmological influence and no influence from other masses, then the metric should become flat, far away from the object. And the Schwarzschild metric is the best known and simplest example of this property of an isolated body. Then the metric is static, and that's a non-trivial result which was found only after Schwarzschild. I already mentioned that Schwarzschild puts this in as an assumption, but actually it comes out from the calculation. You only need spherical symmetry, then it comes out that the metric is static. And the person who found this was the American mathematician George Birkhoff. So that's called the Birkhoff theorem. And if you remember the derivation of the metric, you will remember that at some stage this really came out. So we had 3 metric functions. I called them nu, mu, and sigma. And in the beginning, they were functions of R and of T. We allowed this. But then, upon solving the system of differential equations, at some stage we found they cannot depend on T. They must depend, they are allowed only to depend on R. And that's the content of the Birkhoff theorem. So what exactly do we mean by static? Roughly speaking, we mean that the metric is time dependent. So you see the coefficients depend on R, but they do not depend on T. Yeah? So T is what is called, d by dt is called what is called a killing vector field. A vector field d by dt. Here this Gaussian basis vector field d by dt is a killing vector field. So this what is a killing vector field. And this simply means that the metric coefficients do not depend on T. This has nothing to do with the English word to kill. It is named after a German mathematician with his name. Yeah? His name was Wilhelm Killing. He was a German mathematician in the 19th century. And if this is satisfied, then we say the metric is stationary. Static is more than stationary. Static means also that the surfaces T equal constants, hypersurfaces I should say, they are 3-dimensional. Are orthogonal with respect to the metric to the T lines, to the vector field d by dt. So if you draw a picture, saying here are the T lines, so that's dt. And then you have here the surfaces. You should think of them as being 3-dimensional, T equal constant. and they are perpendicular with respect to the metric. And how do you see this? Well, you can read it from the metric. What does it mean that the surface t equal constant is perpendicular to d by dt? The surface is spanned by the vector fields d by dr, d by d theta, and d by d phi. So the statement is that these three vector fields, d by dr, d by d theta, and d by d phi, that they are perpendicular to gt. And this is obviously true because you can read from the metric that this is the scalar product of d by dt and d by dr, right? GTR. GT theta and GT phi, they are all 0. You can read it from the metric. We don't have terms with dt dr, we don't have terms with dt d theta or with dt d phi. So you can read it directly from the metric. And so these are the two properties. First, that the coefficients are independent of t, and this orthogonality condition. These two things together, they are meant if we say that the metric is static. So if this second condition would not be satisfied, actually, what would then physically be the difference? Well, physically the difference would be that then the thing could rotate. And actually we will encounter the Kerr metric in a couple of weeks, and the Kerr metrics will have such a term, a GT phi. And this will indicate that the Kerr metric describes something which is rotating. It's then, of course, no longer spherically symmetric. Yeah? It's neither spherically symmetric nor static. It's only stationary, but at the moment we have a static metric. So that's the second important property. And here, of course, you see, if we really interpret this as in some way of being time independent, then of course it's essential that we interpret the d by dt as time-like. And that's true only outside of r equal rs. Yeah? Because inside r equal rs, we have a change of sign here, and d by dt is no longer time-like. So then we wouldn't say the metric is static, because t is no longer a time coordinate. Yeah? These properties are still true. Yeah? D by dt is still a killing field inside, and this orthogonality property is still satisfied, but d by dt is no longer a time-like vector field. So inside r equal rs, the metric is not static. So it's only static if this here is satisfied. Okay, this was the second property. Third property, let's talk a little bit about the interpretation of the coordinates. That's always important. If you write down a metric in some coordinates, usually the coordinates have no immediate interpretation in terms of something which you can actually measure. They are just labels of the points. Yeah? And you can choose the coordinates as you like. So when you discuss the physical meaning of a metric, it's always helpful if you are able to associate the metric as a coordinates with a certain interpretation. And actually for the r coordinate you can with the r coordinate you can associate such an interpretation. But we know from the first property that far away from the center, of course, it's our good old r coordinate as we know it from Minkowski space. But in the inner region, in the region nearer to rs, where these terms are not negligible, of course we get a deviation from the flat geometry. And then the question is, what's the meaning of the r coordinate? And the r coordinate gives the measured, really with the metric measured length of circles. I'll point this out in a minute, what I mean by that. Length of circles and areas of spheres. So it does have an interpretation in terms of measurable quantities. So let's consider the first thing first. The length of a circle. So consider a circle. Oops. Where I fix the t. Yeah. So that's some instant of time. T equal t naught. Then I go into the equatorial plane. Theta equal pi half is the equatorial plane in these ordinary coordinates. And then I also fix the radius, r equal r naught. What I get now is something which is parameterized only by phi. Phi is the only coordinate which is not fixed. So the thing what I've determined by these three equations is a circle. It's parameterized by phi. And I can ask myself, what's the length of this circle? And I can read it from the metric. So t is fixed, so this term is irrelevant. R is fixed, this term is irrelevant. Theta is fixed, this term is irrelevant. So the length is given by this term alone. And sine of theta is 1, because theta is pi half. So I just have to integrate r squared. Well, I have to take the square root, because the length is g gives the length squared, right? The length is, so obviously the thing is parameterized, that causes L, and it depends on the radius R0. And it's an integral over the phi, of course. It's parameterized by phi. Phi runs from 0 to 2 pi. And yeah, the measure, the length measure can be read from this term. I have to take the square root of this term. This gives me the length measure here. And this is r, and I am on the circle where I have fixed the r coordinate, so this is just a constant r0. And this is 2 pi r0, as even I can easily calculate. So this is the usual formula for the circumference of a circle, which you know from ordinary Euclidean geometry. So that's the meaning of this coordinate. Yeah? So if you lay out a rope on a circle, and you measure the length of this rope with your metric, really with a physical measure which is used in your space-time, you get the usual formula from Euclidean geometry. And the same, an analogous calculation applies to the area of a sphere. So if instead of this we consider a sphere, so I now fix again the t, but not the theta, only the r. So this gives a sphere, right? It's a sphere at a particular time t0 with a radius r0. And then I have to consider this length, this area element here, which involves the angles theta and phi. So analogous calculation shows, analogous to this one there, shows that the area of this sphere is, let's say, a r0, and this is 4 pi r0 squared. So again, the usual formula for the area of a sphere. So you can use either of these results in order to interpret your R0 in terms of measurable quantities. And because of this property, this Schwarzschild coordinate, as we often call it, is also called the area coordinate. Yeah, because it gives the area of spheres. So in some books you find this name for this coordinate. That's the physical meaning of this coordinate. By contrast, you have to be careful. If you measure the length of a radial distance, so you fix the t and the angles. So then you are on a radial line where the coordinate r is running, and you measure the length of such an interval on the r line, then you will not get r1 minus r2. Let's do this quickly by contrast. The length of a radial segment, so say t equal t0, theta equal t0, maybe any angle, and phi equal phi naught. Yeah, so that's a radial radial line. So a radial segment has length. Let's calculate this. So this is a length. Now it goes from a radius r1 to a radius r2, say. So this would be, I have to integrate over r, and now I have to read the length measure again from the metric. So this time I have to take the square root of this term here. Yeah? If I have such a length segment, only this quantity is relevant. All the other things are 0, and I have to take the square root. So I get square root 1 minus rs of r. It's an elementary integral. You can calculate it, gives something with a logarithm function. I don't know what exactly comes out, but it's fairly sure it's not r2 minus r1. Yeah? It's not the ordinary length which you could read from your coordinates. Yeah? So if you draw a picture in these coordinates, And you consider a certain radial line, and now you measure the length of this radial line just with your ruler. You don't get the physical length. Yeah? So you have to be careful that the length measure in the radial direction is not given by the r. So I don't like the expression that the r gives something like the distance from a center. Yeah, that's a very misleading way of putting it. It doesn't do this. It has nothing to do with the distance from a center. So the physical meaning is that it gives the length of circles and the area of spheres. Okay, so this was a remark on the r coordinate. And what else did I want to say? I think nothing. As to the general interpretation of symmetric, well, that it's spherically symmetric is, of course, obvious because we started from this assumption. Yeah? You can read this from the fact that you don't have a theta or phi dependence in the coefficients, right? So the coefficient, that's the angle element, that's the area element of the spherical of the sphere part. And the coefficients in front of these, they depend on r, but not on theta and on phi. This expresses the fact that the metric is spherically symmetric. And we have put it, when you derive the metric, you put this in at the very first step, actually. So, of course, it has come out in this way. Okay, so this was very few sentences about the physical meaning of the Schwarzschild metric and what you need for the interpretation, where we stayed away from r equal rs. And now we have to discuss what happens if we approach r equal rs. And well, as you probably all know, actually it's not quite as bad as it looks at first sight. What occurs at r equal rs is just a coordinate singularity. It's not a physical singularity in the sense that something blows up, that something explodes or whatever. And yeah, how do you see this? So now the question, what happens at r equal rs? So if we do have a body whose physical radius is smaller than rs, what should we do with the zero in the denominator? Well, there are two possibilities. Let's look at what exactly is a quantity which has a singularity. It's a metric coefficient GRR. So GRR, and what is GRR? GRR is just a shorthand notation for this expression. So this goes to infinity for r to rs. That's the observation. And now there are two possibilities. Either the metric blows up there. That would be bad, because the metric has something to do with really, with physical measurements, with length measurement, time measurement. So if the metric would blow up, that would be bad. But it's also possible that just this vector field blows up. And this would not be so bad. It would just mean that the coordinates are not appropriate near this point. And that's something which is not so unusual. Well, actually, the angle coordinates are the very best examples for coordinates which become pathological at some point, namely on the axis, theta equals 0 and theta pi half. There, these coordinates become pathological. But of course, there's nothing bad on the sphere at this point. It's just the coordinates which are badly behaved. And one could have the hope that this is the same here. And actually, it is the same here. So it's the d by dr which behaves badly. It's not the metric. And you demonstrate this by making a coordinate transformation. And I will repeat this because it's really important in some detail, although I assume that you have seen this before. So a first indication that not anything really bad happens at r equal rs comes from looking at curvature invariance. Yeah? So as curvature invariance, I'll give you an example in a minute. Invariants stay finite at r equal rs. So, for instance, I write an example here in a minute. Oops. One can hope that it is d by dr and not g that blows up. So what is a curvature invariant? A curvature invariant is a scalar quantity which is made out of the curvature tensor. If you look at the components of the curvature tensor, they also the coordinate basis vector fields enter. So this wouldn't tell you much. So if some particular component of the curvature tensor, so say the R0112 component or something like that would blow up, this wouldn't tell you anything. Again, the singularity could come from the basis vector field. But if you, for instance, consider this thing, which is called the Kretschmann scalar, yeah? So you pull the indices in such a way that on one R you have all indices downstairs, on the other you have all of them upstairs, and then you sum over corresponding indices, you get something which is finite. So this here is finite at R equal Rs. You can calculate it. It becomes infinite at R equals 0, but not at R equal Rs. And that would be a good indication. Now, what other scalar curvature invariants you could think of? Let me write this here. Well, that's a little joke. I will erase this in a minute. So what about this here? You could consider this here. It will also be a scalar invariant, right? All indices are summed away. So would this tell you anything about the metric? We are considering the Schwarzschild metric. So what would that be for the Schwarzschild metric? Of course, 0. Here we have a vacuum solution without a cosmological constant. So this wouldn't tell you anything, because just from the field equation you start with, you know that this is 0. So it is a curvature invariant, but one which doesn't tell you anything about the Schwarzschild metric. But this is non-trivial. Yeah? Of course, the curvature tensor is not 0. Yeah? So the curvature tensor, the space-time is curved, it's not flat. Yeah? So the curvature tensor is not 0, and this invariant also is not 0. And it can form invariants also by considering covariant derivatives. So you could put one covariant derivative here, one here, and again sum over the indices. That would give you another curvature invariant. And whatever you try, whatever curvature invariant you try, you get something which is finite at R equal Rs. And that's a strong indication that that this is just a coordinate singularity which can be transformed away. And indeed, the singularity at R equal Rs can be transformed away. And there are various ways in which you can do this. And I will mention, I think, 3 coordinate systems, with four, which makes this regular. So one which you certainly know, I will discuss this soon. Again, these are the so-called Eddington-Finkelstein coordinates. Then there are other ones which you might also know. I had briefly mentioned them in my course on GR. These are the Kruskal coordinates. And then there are 2 other ones which I will briefly discuss, which I think are new for most of you. One is Perlick-Gülstrand coordinates. Gülstrand. And the other ones are the Lemaitre coordinates. I think he has this funny hat over the eye, right? Lemaitre. I think that's the spelling. Coordinates below. Lemaitre is the father of the Big Bang, right? He invented the idea that he didn't use the word Big Bang, but the idea that our universe started with a Big Bang. This was suggested by Lemaitre in the late 20s. Abbé Lemaitre, so he was a Catholic priest. A little bit unusual for a scientist, but there were some of them. Okay, so I will talk about this now in quite some detail. So now we will, this was section 3, so we will now do a subsection Schwarzschild metric and other coordinates. And I will mention quite a few of them. Actually, I will only transform the R and the C. I will never do anything with the theta and the phi. Yeah, we have a spherically symmetric situation, and why should we do anything else with the spheres and parameterizing it by theta and phi? There's no reason for this. This wouldn't help in any way. But we can play around with the R and with the T. So these coordinates we started with, the T and the R, are the ones which are best adapted to the symmetry. But there are other properties which are not so well shown. For instance, the behavior at r equal rs. This is not at all well shown. So there are various reasons for introducing other coordinates. I will begin with some simple coordinate transformation where I just transform the r. This will not help us much in view of r equal rs. It will just move it around on the axis, but it will not change much of the properties. Then I will talk about one coordinate system where the t is changed. That's the Eddington-Finkelstein. There's a t is changed and the r is kept. And then I will talk about coordinates which mix them, which change both of them, the r and the t. And these are the most interesting ones. So I will begin with a coordinate transformation where just the r is transformed. So this doesn't help in view of the singularity. And this is called the isotropic coordinate system. So in this case, our all coordinates were t, r, theta, and phi. And what we now do is we transform only the r. So we get now coordinates t, r, tilde, theta, and phi. And how is this defined? So the r tilde is defined as 1/2 square root of r squared. I wrote 2m here. Our notation is rs. Sorry. Rs is a Schwarzschild radius. Yeah, if you do I have it still on the board? Where is it? Here is it. Rs. Usually, old-fashioned people like myself work in units where g and c are set equal to 1, and then the Schwarzschild radius is just at 2m. Yeah, so very often you find in books and in articles that instead of the rs, just 2m. So, but here in this lecture, I try to always stick to my notation. So then I have here r minus rs half. So that's a transformation. Yeah. So you see, the new r is just a function of the old r. The other three coordinates are not involved. And if you juggle this a little bit around, then you can solve it for r. So the equivalent version now solved for r is that this is 2r tilde plus rs half squared over 4 r tilde. And now we can calculate the metric in these new coordinates. Let me see. I have 6 minutes. I think I can just manage doing this in these 6 minutes. Oops. So what I need is, I have to replace in the matrix the r by this expression. I also have to replace the dr. So we have to calculate the dr. Let me see if I can do this. 2 times 2r tilde plus rs half, 2 times dr tilde. That's the derivative of the numerator, right? Divided by 4 r tilde. And now minus, I differentiate this here. 2r tilde plus rs half squared divided by 4 r tilde squared, dr squared. I think I should put this on one denominator. So then I have 4 r tilde squared. So I have to multiply this with r tilde. I think I can divide by 4. Yeah, maybe that's a good idea. And 2 squared is also 4, and then I have a 4 here. Yeah, may I do this in this simple way? Okay, so then I have only an r squared, r tilde squared here. And now I multiply with r tilde. So this gives 2r tilde squared plus rs r tilde half. And here I have, if I multiply this out, minus r tilde squared minus r tilde rs half minus r squared over 16. I think I can simplify this a little bit. This goes away, and this goes away. Not too bad. So I'm left with, let me continue here. dr is what? dr is r tilde squared minus rs squared over 16. And I forgot the r tilde, right? Divided by r tilde squared. Okay, I insert this into my metric, and then I get what? Here I had minus 1 minus rs over r. Rs over r, and for r I have to substitute this rubbish there. Rs times 4 r tilde divided by 2r tilde plus rs half squared, c squared dt squared. Okay? Oop. Now, the r squared, that's what I've just calculated here. So this thing squared, this gives, here I can use the binomial formula, right? So this is r tilde minus rs over 4 times r tilde plus rs over 4. And the whole thing is to be squared because I need the r squared. And here r tilde to the 4. dr tilde squared. So that's the dr squared. And then I need the denominator. The denominator is just this here, 1 minus rs over r. So I have to put this here again. 1 minus 4 rs over r tilde 2r tilde plus rs half squared. And here I have r squared. I read it from this expression. R squared is that true? Well, let's see what we get. 2r squared plus r is half squared. And the whole thing squared again, so it's to the power 4. That's wrong. Wait a minute. What did I do there? That looks funny. Let's see what we get. But that's it, right? d theta squared d phi squared. It could be, yes. 2 to the 4 is also 16, so it's not quite as crazy as it looks. So here, if I continue, let me write this on a common denominator again. Then I have 2r tilde plus rs half, the whole thing squared. And now I multiply this out, then I get 4r tilde squared plus 4 over 2 is 2 tilde rs plus rs squared over 4 minus 4 rs over r. Okay, this gives a 2 here, right? This should give a nice expression. Let me see if this works out. R tilde is rs 4 squared. R tilde rs 4 squared. And now I put this in the numerator. Then I get, if I take the 4 out of the bracket, I get 4 times this again squared. So it's now to the power 4. And in the denominator, sorry, I have 4r tilde squared plus 2r tilde rs, rs squared over 4 minus 4rs over r tilde. Again, these two terms cancel. I think I can't do anything with this here. Maybe it takes a 2 out of the bracket, then it goes away in comparison to the 16. And I get r tilde plus rs over 4 to the 4th. The 16 is gone, and I have this here. Okay. Let me see. Is this a square? Yes, I think this is a square, right? Yes, this is a square. This is 2r tilde minus rs half squared. Very good, very good. Here, again, I think I cancel the 4. Then I have r tilde squared. That's a square, right? R squared minus rs half squared. And here I have divided by 4, so I get R tilde plus RS4 squared. Very nice. That's the first term. The second term is I copy the denominator as the numerator. R tilde minus RS4 squared. R tilde plus RS4 to the 4th. And the 4 I cancel. Then I have here R tilde to the 4. And this is again a squared. R tilde minus RS over 4 squared. And you see very nicely these two terms go away. And I forgot the dr tilde squared here. I just forgot to copy it. And the other term, the last term, is this here. And now you see what was the idea behind this funny coordinate transformation. Namely, the spatial part of the metric has now become very nice. Yeah, you have here the same factor, up to an R tilde squared, but that's what you need for the angular part. So you can combine these expressions. There was a minus sign in front, right? I forgot this. Minus R tilde minus RS half squared, R tilde plus RS half squared, T squared. And now I combine these two terms. I forgot again the dr tilde squared. I write this term in front of everything. So I have R tilde plus RS over 4 to the 4th, R tilde to the 4th, and our bracket dr tilde squared plus R tilde squared, because here I have a 4 and I need only a 2, right? So I have to multiply this with R tilde squared, d theta squared plus sine squared theta, d phi squared. And now you see there's a good old friend here. What is this? This is just the flat metric, the flat Euclidean metric in spherical coordinates. So this radius coordinate has a nicer meaning in view of comparison with the Euclidean metric, with a flat metric. So the spatial part of the metric is now a factor times the ordinary Euclidean metric. And well, this is what is called a conformal transformation. Yeah, if you multiply a metric with a scalar factor, then you say you make a conformal transformations. And conformal transformations have the nice property that they preserve angles. So if you measure angles, if you read off from your picture angles in this coordinate system, then it's really the angle measurement which is used in your space-time with a physical metric. Yeah, so if you draw orbits, orbits of planets or something, and they intersect each other, not at right angle, at some angle. If you do it in Schwarzschild coordinates and you read just this angle, you measure it with your protractor, what it gives you doesn't tell you anything about the real angle between the orbits. Yeah, it's just a coordinate picture. But if you do it in these coordinates, then it's really the angle as it is measured with physical means. So this is very nice for interpreting the spatial geometry, in particular if angle measurements are involved. Okay, I think I should stop here. I'm already 5 minutes over time. And I will continue then next week with the Tertius coordinate and then with the Eddington-Finkelstein and so on. And we will discuss the isotropic coordinates in one of the worksheets, in the next worksheet. We will do a little bit with this. Okay, so I say goodbye to everybody who is watching this recording, because now we switch off the camera and the microphone and we do the tutorial among ourselves now in a relaxed atmosphere. Okay, see you.